In the animal kingdom, yes, it's supposed to be an M. The symmetry of an animal's body is often an indication of the animal's complexity. Animals displaying line symmetry, such as insects, are usually more complex life forms than those displaying rotational symmetry, like a jellyfish. Okay, so off to the right there, this beetle here, or bug, or insect, whatever, okay, it does have line symmetry. So if I were to fold it in half, it would be dead. It would reflect onto itself. Okay? The jellyfish off to the right there has multiple lines through it. Okay? It has this rotational symmetry. So if you were to rotate it around on itself, it would land in the same spot. Okay? So we are going to go over line symmetry, rotational symmetry, plane symmetry, and axis symmetry today. They're all kind of similar. So first one I want to go over is line symmetry, which you have probably seen before. So a figure in a plane has line symmetry if the figure can be mapped onto itself by a reflection in a line called a line of symmetry. Okay, so if I can reflect something onto itself, it has this line of symmetry. It's symmetric on both sides. So in our examples below here, we want to state whether the object appears to have line symmetry. If it does, we want to draw in those lines and state how many there are. Okay, so for letter A, your line is already drawn in. So letter A does have a line of symmetry. It's through the center and vertical right here. Okay, so it is the same on both sides, that line of symmetry. That is the only one that can get drawn in. So I would say this has one line of symmetry. Okay, so that one has one line of symmetry. Again, B, this one, the lines are also drawn in. This one has multiple lines of symmetry. Okay, so I have a vertical one right here. Another one here. That's two. Okay, a third one right here. A fourth one right here. And a fifth one right here. Okay, so over each of those lines, that star will reflect onto itself. Okay, so this one has 5 lines of symmetry.
You call it a star?
It's a starfish. Sorry.
You know, I caught one in Florida, and it's little feelers.
They like do this.
They're all in.
Yeah.
Oh, that one got full.
They're multiple times.
Letter C. Letter C. Am I able to draw in any line where that would reflect onto itself?
No.
No. So this one has no lines of symmetry. Okay? So that one has no lines of symmetry. Questions on the first 3. Okay, I want you guys to do D, E, and F. Okay, so decide if it has a line of symmetry. If it does, draw it in and state how many there are. Okay, you can talk to each other if you need to.
Said no. What did you say?
I just sent you. I said there's 4. Oh, we sound like a dog.
No, well, I don't know. Yeah, that was good.
I said 4.
If it's Now if it was a oh my god. I don't know.
Maybe.
What? What is it? Is it 4?
No. All right, so looking at letter D. Letter D has no lines of symmetry.
Yes.
Told you I had no.
So this one's always confusing for most people, so I have a parallelogram kind of cut out here, right? I know some people did get this one right as I walked around. Now, if I were to fold it along the diagonal, this is what happens. It doesn't fold onto itself, okay? If I try and fold it on the other diagonal, again, still doesn't fold onto itself. If I try and fold it in the middle, still doesn't fold onto itself. Okay, last one in the middle here, still doesn't fold onto itself. Okay, so this one has no lines of symmetry. There's no way you could fold this where it would map out onto itself.
Symmetry. The whole thing.
I bet you this one has 1. Forgot which one.
All right, so letter E, this one does have 1 just because all your sides aren't congruent to each other. Okay, if all of your sides were congruent and all your angles were congruent to each other inside there, you would have 5. But you just have 1 since this angle is larger than this angle here.
I don't know if I'm on this story.
Okay, so this one has 1 line of symmetry. Again, it's because those angles aren't all congruent to each other on the inside of that figure. Okay, letter F. How many lines do you have? 2. 1 vertical, 1 horizontal.
That line is straight.
I know.
Mine is straight.
It's alright, mine
Mine's
looks like
curvy.
it.
Squiggles.
Okay, so last one has 2 lines of symmetry. Any questions on your lines of symmetry? You can't do it on the diagonal. If it was a square, you could do it on the diagonal.
I know one of the 4-sided ones has 4.
All right, so next, we're going to move into rotational symmetry. Please make sure you're paying attention to this one. Okay, so a figure has rotational symmetry if the figure can be mapped onto itself by a rotation between 0 degrees and 360 degrees about the center of the figure, called the center of symmetry.
Center.
Okay, so we're taking our figure, we have this center point, and we're rotating around that center point and seeing if our figure matches up to itself. Okay, so in a square, in this example below here, we're going to ignore 0 degrees and 45 degrees. Okay, your square has a rotational symmetry of 90 degrees, 180 degrees, and 270 degrees. Okay, so I could rotate this entire square here 90 degrees this way, and it will map out onto itself. I could rotate it 180 degrees, and it'll still map out onto itself. Same thing with 270 degrees. That entire square just spun all the way around to 270 degrees, still maps out onto itself. Now we don't include 360 degrees, because every figure you could rotate 360 degrees and it'll map out onto itself. Okay? Because it's a whole circle then. So we don't include 0. We don't include 360. However, we need to be able to find what that degree measure is. Now, looking at this, a square has 4 sides, correct? A full circle is how many degrees? 360. So to get this 90 degrees, we take 360 and divide by how many pieces we have within it, and this one is 4. Okay, so that's where we're getting this 90 from. From there, all you have to do is continue to add 90. So I add 90 to 90, I got 180. I add 90 to 180, I get 270. Okay, so you continually add that degree measure to each one to see what that figure can rotate through. Questions before we do an example?
It's a 360 divided by 2 would be 180.
Yes.
And then 360 divided by what? How would you get 270?
You're adding 90 to this each time. So add 90 to 90. Add 90 to 180 to get 270. So you're adding this answer, which is 90, to each one. So 90 to 90 is 180. 90 to 180 is 270. All right. So here we're deciding whether these have rotational symmetry. Now if they do, we have to locate that center of symmetry, so the center point that's rotating around. And we have to state the order and magnitude, just meaning we have to state the degrees that it rotates through. Okay? So letter A, does this one have rotational symmetry by just looking at it? Could you rotate it around and it land on itself? Yes. Okay, so we do have rotational symmetry. You can write yes. I'm just trying to be more specific. So, it does have rotational symmetry. Now, how do I find the degrees that it's going to rotate through? What should my first step be? You want to see how many pieces are within your figure, right? So here's my center. Okay, I could cut this into different slices. So I could cut this into 6 different slices. So to find the degrees that it rotates through, I'm going to take my total degrees of a circle, so 360, and divide by how many slices I have, which is 6. That's 60. So our starting degree is going to be 60. So I have rotational symmetry of 60 degrees. Okay, to get my next degree, I just add 60 to that. So I keep adding 60 to each one. So I have 120 degrees. Add 60 to 120. 180. Add 60 to 180. That's 240. And add 60 to 240. That's 300. Now I do want to stop at 300 because with rotational symmetry, you're looking for those degree measures between 0 degrees and 360 degrees. If I were to add 60 degrees onto 300, I would get 360. Okay, and we don't want to include 360, and we don't want to include 0. So I would stop at these 5 different degree measures this could rotate through. Questions? Questions? All right, then letter B. Could I rotate this any degree measure and it map out onto itself? No. So this one does not have rotational symmetry. Okay? So B does not have rotational symmetry.
Actually, you can rotate.
What can it rotate? What can it
180.
rotate? So letter C. Letter C does have rotational symmetry.
Just watch it. We really
Okay.
have to write rotational.
No, you can just write yes.
Write yes or no. So I'll
You
write
can just
no.
write yes or no. Okay, so this one does have rotational symmetry. It is 180 degrees. So here I could map out my center. Okay, if I split this in half here, I would take this piece and I could just rotate it 180 degrees around and it would land on this piece over here. Okay, so it would only be 180 degrees.
That reminds me of the Christmas candies. Like they're all like. They're never seen those. What? They're from like the 90s. Oh. They're like. Sorry. They're like hard licorice. It is like licorice, but they're hard.
It sounds familiar, but I don't know. Okay, questions on A, B, or C?
Nope, but I'm not doing D by myself.
Yes, you are. So you guys are going to do letters D and E. So decide if it has rotational symmetry. If it does, you need to find the angles that it can rotate through. Okay, so those degrees that it can rotate through.
This does not look like
This one 270.
Huh?
Something divided by
360.
it's a no.
You can't.
You can't.
E
It
is
looks the
definitely a no.
same. You can rotate.
I don't know.
It can rotate
It's like a Dora flower.
5 times. What's 360 divided
You
by
gonna take a good look?
Did your wife be nasty?
No, actually, can you pick
But this one's
this?
This will follow the same.
Someone tell me what 360 divided by 5 is. 72. It goes two times. She knows her stuff. She's a math teacher.
Well, there's 280.
He went.
Where's the no?
That one's no. Look at those pedals. You can tell them.
Actually, it's yes.
What part are you singing in that song?
72 times 2.
Yes and no.
Yes and yes.
What time is it? Oh my god, work it. Come to sense after.
No, I'll get ready to send me I want to print my notes too. I'm not going to now, because I'm going to be there all night. And Terry wants me to go because somebody's trying to show up to go.
Terry said that?
Where's you going?
Wait, you got invited? No.
Where's you going? You can come with me.
Right, because if you do it 5 times,
Yeah.
you gotta
I
do it 6.
need
I thought you
You're gonna drink?
Add a
Here, you're gonna drink.
Get a drink. Get a drink.
Sure.
What did you? Bro, if I do, well, I'm not.
Drinking's not cool.
You can say it live.
Or you can say it right now.
and then write that last one down.
I'm serious.
I fucking know about it. I had like thought about it.
Yes.
5 years and then sounds like you're going to party about
Right.
it.
So like this one, right?
Bradley knows
No,
everything.
literally, like, my mom was like, because my mom, well, she did this one. She's like, yeah, well, my dad should give it to her someone. My dad's one.
Your thing's not really cool.
Did you see blood go up on that napkin?
Well, she told me that.
What?
So that was only on
It's not their house. Yeah.
Send somebody to Bradley too.
your petals here.
Bradley wants to go, but he'll probably bring it. But what time is it? Right after graduation. I have to go to after graduation. Are you wanting to actually graduate? Are you going to actually graduate? I'm working for it. Yeah. I took
I don't like
All right, we're gonna go over D and E. So, letter D, you do have rotational symmetry.
Oh my god. January is my graduation because that's the day of my confirmation. That's the day of my confirmation. And then that
Quiet now, please. So letter D has rotational symmetry.
Yeah, but that one petal is not the same.
Okay, they're all supposed to be the same.
Okay.
So here would be your center of symmetry. Okay, and I could split this into 5 different petals. Okay, so to find our degrees, I would take 360 divided by 5. That is 72. So we have rotational symmetry of 72 degrees. We want to find out the other degrees that it rotates through. So add 72 to 72. It's 144. Add 72 again to that one. And add 72 to that one.
288.
It's 288, dude.
Okay, if I were to add 72 again, I would get 360. Okay, we don't write 360 because every shape would have rotational symmetry then.
And E is just like, it's really cool.
Quiet, please. So letter E does have rotational symmetry. Okay, this one does have rotational symmetry. Its center is right here.
I just find the class so far.
I can split this into 3 sections. So each section includes a large petal. Each section includes a large petal and a small petal. Large petal, small petal, large petal, small petal. Okay, so I have 3 different sections here. So to find the degrees that it rotates through, we take 360 divided by our separate sections here, so 3, and that's 120. So we have rotational symmetry of 120 degrees. Add 120 to that. That would be 240 degrees. And we stop because the next one would be 360. Okay, questions on rotational symmetry? Do you have a question? No. Okay. All right, off to the right there, I have something called point symmetry.
Point symmetry.
A figure has point symmetry if the figure can be mapped onto itself by a rotation of 180 degrees. So a playing card exhibits point symmetry. It looks the same right side up as upside down. What was the example of point symmetry in our 5 examples above? Which letter from above here was an example of point symmetry? No.
Oh, C.
C.
C. I see. Get it? I see.
So point symmetry. It can be mapped onto itself by a rotation of 180 degrees. Okay? So it just has 1 point. You could split it just in half. And as you spin it around, it's the same upside down as it is right side up. Just like a card. Okay. The next 2 are symmetries in 3-dimensional shapes. So you probably have not covered this ever before. So please make sure you are paying attention. So plane symmetry
It's just plain.
is a three-dimensional figure that can be mapped onto itself by a reflection in a plane. Okay, so you have this plane that's going to cut through your three-dimensional object, and it's going to be the same on one side of that plane as the other side of that plane. Okay, the next one is axis symmetry. Okay, so that's a three-dimensional figure, can be mapped onto itself by a rotation between 0 degrees and 360 degrees. Okay? You guys are never going to get your homework.
Yeah.
So, axis symmetry, you're taking a figure, rotating it, and mapping it back onto itself just like rotational symmetry, except now it's a three-dimensional figure instead of two-dimensional. Okay? Same thing with plane symmetry. Plane symmetry is very similar to line symmetry. Okay, so it's if you could fold it over onto itself, it's the same on both sides. So you're looking for that plane that would cut through it where it's the same on both sides of that plane. Okay, so we're going to do the next 4 examples here. So we want to state whether the figure has plane symmetry, axis symmetry, both or neither. So in letter A, this is our three-dimensional shape. We want to decide if this has plane symmetry. So can I cut through this shape where it's the same on both sides of that cut?
Negative.
You can cut straight down the middle here.
Oh, yeah.
Okay, if I cut this vertically and straight in the middle, in that L shape, it'll be the same in the front as it is in the back of that plane. Okay, so I can cut through it straight down vertically. It's the same in the front as it is in the back. Okay, so this one does have plane symmetry. What about axis symmetry? Is there any way I could take this three-dimensional shape and rotate it around where it's going to map out onto itself? No, there's not. So this one does not have axis symmetry.
The next one does.
Wait, why? Wait, oh.
Because I can't rotate it around itself and it's not going to be the same. Okay, questions on the first one? All right, then letter B. In this one, I want the bases of this to be congruent. Okay, so all of these sides are going to be congruent to each other in that pentagon. So, is there any way I could slice this three-dimensional shape with a plane and have it be the same on both sides of that slice? Yes, there is. Right down the middle here.
Told ya.
Okay, I could just split it right in the center, and it'd be the same on both sides there. There's another one. Not vertically, but horizontally. Right in the middle, horizontally here. Okay, so I could split this right in the middle, horizontally, and it's going to be the same on the top as it is on the bottom of that plane. Okay, so this one does have plane symmetry. What about axis symmetry? Could I spin this and get it to the same spot or mapped out onto the same figure? This one does have axis symmetry. Okay, so in this one, if this is my center point and all of my sides are congruent here, okay, I can split this into equal sections. Okay, there are 5 equal sections there. And if I just spin it vertically around each of those sections, it's going to map out onto itself. So just like with rotational symmetry, I want to find the degrees that it can rotate through. So to do that, I created those 5 sections still. So we take 360 and divide by our 5 different sections. Okay, so this will have axis symmetry of 72 degrees. What's our next?
144.
144.
260. 288.
Okay, so just like with rotational symmetry, with axis symmetry, you still want to find those degrees that it can rotate around. Okay, so I could rotate this entire figure. If I had a top and I rotated it 72 degrees, it would land back onto itself. Make sense? Yeah? All right, letter C. Does this one have plane symmetry?
No.
Does it have axis symmetry?
She's lucky it wasn't me.
Okay, so shh. Letter C does not have plane symmetry, and it does not have axis symmetry. You cannot slice it down the middle. You cannot rotate it around itself. Okay, then letter D. Is there any way I could cut through that bat with a plane? Yes. We can cut through it horizontally. Okay, and it will map out onto itself. Okay, so this one does have plane symmetry. What about axis symmetry? So if you take a baseball bat, you take a baseball bat, you stand it up straight. If I spin it with my fingers, is it going to map out onto itself?
Yes.
Yes. If I spin it more, is it going to map out back onto itself?
Yes.
If I rotate it 2 degrees, is it going to map out onto itself?
Yes.
Yes. It has axis symmetry because you can rotate it around itself and it still stays in the same spot. So this one does have axis symmetry. Now, like I said, the top part of that bat and the bottom part are circles, right?
Yep.
They're circular. So I could rotate it 1 degree. I could rotate it 24.5 degrees, right? And it still map out onto itself. So to write out the degrees that it can rotate through, we would say this has axis symmetry for angles between 0 and 360. Because we are looking for, if you look back in the definition of axis symmetry, it has to be between 0 and 360. It can't be equal to 0. It can't be equal to 360. It can't be over 360. So it's all those angles between those two numbers. Okay, so if you have that circular base and you know you could just spin it on the top, any degree measure, that's how you would write that out. Any questions?